Welcome back to another KotlinBytes video. Today I'll show you how to use Kotlin lambdas to express and solve for the derivative of a function at a point. Let's get started. Here I have a simple lambda that takes a double as a parameter and returns a double as a result. This function is just a simple x squared polynomial. Let's test this out at point 7. There we go, 7 squared is 49, as expected. Okay, let's manually derive this function. As a comparison later on, using the power rule, we find that this function's derivative is 2x. Testing this shows us the derivative of the function at point 7 should be 14. Now, let's visualize what's happening to help us build a function that will perform the derivative at a point. The red line is x squared. The black line is its derivative. We can see the relationship between these two lines by graphing a third green line tangent to the red line. The blue line marks the point where the green line is at tangent. At x equal to 5, the derivative of x squared is 10. The derivative should match the slope of our green line tangent. And yes, it does. Therefore, if we can find the tangent line to the red graph using code, we can then use its slope as the derivative of the given x value. Let's try to approximate this tangent line. We'll take 2 points from the original function, let's say f of x and f of x plus 1. These 2 points will form a right triangle that we can then use to determine the slope. The slope is rise over run, or in other words, f of x plus 1 minus f of x all over 1. This line approximates our tangent and therefore is not exact. We can see that the slope is 15, whereas the true derivative should be 14. Here is a good place to start. Let's try to code this. Let's create an extension function on all lambdas that follow the following pattern. Double in, double out. We'll call this lambda once at x plus 1 and once at x. Notice that we're divided by 1. This will make more sense in a bit. At the moment, 1 represents our run, or the space in between our two function calls. When we run this, we'll see that we end up with 15, just like our graph predicted. Coming back to our graph, let's try to make this prediction better. Adjusting the distance between these 2 points drastically affects our approximate tangent line. If d is too large, our estimate becomes worse. However, shrinking d close to 0 seems to help our approximation. This is actually the definition of a derivative. D cannot become 0 since our slope definition is d in the denominator. However, it can be very close to 0, and that is exactly what we're going to do. Let's first create a constant called diff to represent the separation of our 2 points. Then let's change our diff value to 0.5. Yes, the approximation is much better with this, but we can do better. 0.1 seems to be almost there. How about 0.0001? Yeah, that seems to be very accurate. It's still not exact, but that's fine. This was only supposed to be an approximate value anyway. The beautiful thing about this formula is that it will work for nearly all continuous functions, making it a very potent tool to wield if necessary. It should be noted that diff shouldn't be too small. If it's too small, you'll run into computational limiting rounding errors that will cause this estimation to actually become worse. In a later video, I'll show you how you can use this function to calculate other values, such as the square root. Well, that's it for this episode of KotlinBytes. Thanks for watching. If you like what you see, please like and consider subscribing. Source code and additional resources are in the comments below. If there's anything you would like me to explain in a later video, please message me or leave a comment. Otherwise, have a great day.